Alright, today I'm going to talk about periodic trends and a little bit about why we are interested in learning about them and exactly what they can tell us. Before we really get into periodic trends, there are some terms that you should know. The first of these trends is valence electrons. And so what these are the electrons that are found in the outermost energy level, right? Those furthest from the nucleus. These are the electrons that are actually doing the chemistry when we talk about chemistry. So this is why these are important ones to know. We'll definitely talk about valence electrons more in the rest of this class. The second one's going to be effective nuclear charge, right? And so what this is how much of a pull from the nucleus the valence electrons are actually feeling. This is going to be really important for understanding all of the periodic trends, and it's really central to why the trends are what they are and why the elements react the way they do. The next one, shielding. So this is when the core electrons, right, and these are any electrons that are not valence electrons. This is when they block nuclear charge from reaching the valence electrons, right? So it's kind of like they're shielding some of that nuclear charge from those valence electrons. And the last one, electron-electron repulsion, right? This is just talking about how electrons, they're all negative, and so they repel each other, right? Just like two same poles on magnets, when you try and push them together, they're going to repel each other. That's what we're talking about here. So the first trend here, atomic radius, and it is just what it sounds like. It is the distance between the center, or nucleus of the atom, and the valence electrons right at the outside. So it is the radius of the atom. The general trend is that it decreases across a row, right? So going this way, it's going to decrease that way, and it increases down, right? So going this way, it's going to get larger. And that's about it. This really is because that nucleus, right? If we remember what our atom kind of looks like, we've got the nucleus there, and we've got the energy levels. That as we are adding energy levels right here and adding electrons into them, right? If you've got electrons here in the center, those are pretty close, right? The radius is not going to be that large. But as you're adding electrons further and further out, right? If you're adding electrons out here on this third energy level, right? Not only are they going to be further away, but that pull from the nucleus, right, is going to be less the further out you get, right? So these ones here are really close. These ones out here are further away. There's less pull. There's more shielding from those inner electrons, right? And so the effective nuclear charge is less, which means that your radius is going to get larger. Now, why the radius decreases as you go across, right, is because remember that atomic number is related to the number of protons, right? So number of protons here. So as you go across this way, right, you're adding electrons to this outer ring. So the electrons are not getting any further away. They're always at the same distance. However, every time you add an electron, remember you're also adding a proton in here. So you're adding nuclear charge. So actually, because you're adding electrons into the same energy level, and you're adding protons, right, the pull is getting stronger between the nucleus and those outer electrons. So it actually pulls that energy level closer to the nucleus as you're adding protons across a row. All right, and so that's why this trend is the way it is. The next one is ionic radius. Again, just what it sounds like. And this one, it's going to have the same trend. It's just that it's divided into metals and non-metals, right? Radius is going to increase as you go down, and decrease as you go across that way, right? For both metals and non-metals. Now, the thing to remember about ions is that cations, right? Your cations, they are smaller than neutral. Right, and why this is because to make a cation, a positive ion, you are losing electrons, right? And as you lose electrons, you don't lose protons. The pull on those electrons gets stronger, and the radius decreases. Now, it's going to be the opposite for anions. Anions get larger than neutral. Right? And so why this is because you're adding electrons to make a negative ion, and you're not adding protons, right? So that pull from the nucleus actually gets weaker as you add those electrons. All right, so again, effective nuclear charge, determining the trends for ionic radius as well. Next one, ionization energy. And this is the energy required to remove the outermost electron from any atom, right? So again, if we draw our atom here, if we've got electrons out here, it's going to be removing the outermost electron from an atom, and it's the energy required to do that. So this trend, as you go across here, it's going to take more energy, right? Notice the small arm here, the really beefy arm over here, right? And as you go down the periodic table, it's going to take more, or it's going to take less energy, right? So more energy as you go across the table, less energy as you go down the table. And again, all about effective nuclear charge, right? When you have low effective nuclear charge, like over here, it's going to be easier to pull electrons off than when you have high effective nuclear charge, like over here. That means the nucleus is pulling harder. It's going to take more energy to pull that electron off. Also, as you go down, right, as the electrons get further away, they're going to be easier to pull off because the nucleus is not pulling as hard, right? So it all comes back to effective nuclear charge, and it's related to radius. So the last one that we'll talk about is electronegativity. And so what this is a measurement of how strong an atom pulls electrons to itself when it is in a bond, right? Those words are really important. And why is because as this only occurs in bonded atoms, the noble gases, right? This last column over here, we've got, neon, argon, krypton, xenon, right? All those great elements over there, they don't make bonds, so they have no electronegativity, right? Now, this, right, the trend, electronegativity, again, increases across a row, decreases down a column. And it has everything to do with effective nuclear charge, right? When you're over here at fluorine, which is the most electronegative atom, right, it's got a really high effective nuclear charge. Its valence electrons are not far away from the nucleus, and it doesn't have many core electrons, right? So really strong pull on those outer electrons. When you get down here, right, francium, this one, very low electronegativity because its valence electrons are really far from the nucleus because it's got all these energy levels, plus it's got a lot of core electrons shielding. So not very strong electronegativity. Now, how are all these related? I've talked about this a little bit, right? It all comes back to effective nuclear charge. And thinking about it, you notice that as atoms and ions get larger, they're easier to remove electrons from, and they pull electrons in a bond with less force, right? Further away the nucleus is from those electrons, the less force it's going to pull with, the larger the atom or ion is going to be. And so as valence electrons get further, right, the pull from the nucleus gets smaller. It's all about effective nuclear charge. So why do we bother learning about this? Right? This really helps predict how reactive an element's going to be. Right? Those with very high or very low electronegativity, right? Like if we've got our periodic table here, right? The stuff over here that's really highly electronegative and the stuff that's over here that's very weakly electronegative, those are both super reactive, right? Because these are going to want to lose an electron, and these over here, they're going to want to gain an electron or electrons. And so they tend to be extremely reactive, especially with each other or with something that's going to lose or accept an electron very easily. Periodic trends can also help us determine what type of bond will be formed when two elements react, right? Ionic, polar covalent, or nonpolar covalent. We're not going to talk about those today. I will come back to those when we talk about bonding. And they help us to understand the patterns in elemental properties like melting point, boiling point, and density. If we take a look at this slide, all right, we've got three of the trends we talked about: atomic radius, electronegativity, and ionization energy. And if you look at the relation between these and melting point up here, right, you can see that things that are very strongly electronegative or very weakly electronegative have pretty low melting points, right? They're not going to want to stay as solids. Again, things with very high and very low ionization energy also, right, have very low melting points. Again, atomic radius, those with very small and very large atomic radiuses have very low melting points. All right, and the stuff that's in the center here has these high melting points, right? If we look, I think it's only moderately, it only takes a moderate amount of energy to remove them. Their atomic radius is somewhere in the middle. Electronegativity, they're kind of, in the middle. So again, right, having these high melting points, right, being very strongly attracted to each other, corresponds with, middle of the road on all these trends. And so that's how all this stuff is connected. So when you're thinking about things to remember from this, right, effective nuclear charge is central to why all the trends work the way they do. Electronegativity is important to remember, as we'll come back to it and talk about it again throughout the year, especially during bonding. The trends help us understand and predict elemental properties, and that the trends are directly related to the electron configuration in the atoms. So there you go. That's periodic trends. We will have some work to do with this, and I will see you in class.